Hello, in this video we're going to show that r and theta are independent in polar coordinates after a variable transformation. So here we're going to let x and y be independent normal zero sigma squared random variables. So that's a mean zero constant variance sigma squared. We're going to define the random variables r and theta by this transformation. R is equal to r cosine of theta and y is equal to r times the sine of theta. Now first we want to find the densities for r and theta and show that they're independent. And here's the answer. So the densities for x and y are this. They're normal zero sigma squared random variables. They're independent, so their joint distribution is the product of the two, which is this. Now the Jacobian of this transformation is the absolute value of this determinant. And so the partial of x with respect to r, and perhaps that should be a capital R, and we get this, right? So with respect to r, it's just cosine. Y with respect to r is just sine. And then this is the partial of x with respect to theta, so it's minus r times sine of theta, and etc. So the determinant is this times this minus this times this, and you get this equation here. Now an r can be factored out, and then the cosine squared of theta plus cosine or sine squared of theta is 1, so we just get r. Now the joint density of r and theta is this. So we have 2 pi sigma squared, and this r is actually from the Jacobian. And then we plug in x and y here. So that becomes r squared cosine squared. And this is r squared sine squared. Now again, we can factor out an r squared. And then the cosine squared of theta plus sine squared of theta is 1. And so then we get this as the joint density for r and theta. Now to find the marginal distributions, we have f of r. And we're going to integrate out theta. So we go from 0 to 2 pi of this joint density d theta. Now here in the joint density there's no theta, so it's constant, so it can be moved out front. So we just get this constant times theta and evaluated at 2 pi and then minus 0, and that, of course when that goes away at 0, so we plug in the 2 pi, those cancel, and we're left with this. So that's the density for r. Now to find the density for theta, we integrate out r, so it goes from 0 to infinity. And we're going to do a variable change. Let u equal r squared 2 times sigma squared. So du is equal to r over sigma squared dr. Then when you plug this in for the joint density, it becomes this. Now the limits of integration are still from 0 to infinity, but we get 1 over 2 pi e to the minus u du. So then the antiderivative becomes minus 1 2 pi e to the minus u, evaluated at 0 infinity. When you plug in infinity here, this goes to 0. Plug in 0, and you get 1, but it's minus that, so you get minus 1 over 2 pi. And since the joint density is equal to the product of the marginals, they're independent. And that's what we wanted to show. That's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.